Welcome to the Constraint Sequence and Index Management lesson, the last one fully dedicated to DDL commands. Before we dive into today's topic, let me take a moment to congratulate you as you've come along an important journey so far. You are now familiar with a number of different database objects. The objects were purposely grouped as container objects, or as we call basic objects, comprising databases, schemas, and table spaces, and schema objects, which are objects logically arranged within one or more schemas. This is a much larger group, comprising tables with their column definitions and constraints, sequences and indexes, and many more. This lesson finishes a cycle of two groups of lessons. The first covering how to create these two categories of objects, and the second how to manage and modify them after creation. All database objects are more niched or advanced, so it wouldn't make sense exhausting them all before you can play around with what we've learned. Now that we explored the basic table structure management, let's expand it with constraint management to finish the most important outer table actions, especially table-level constraints that allow us referring them directly, without having to nest them below outer column actions. Secondly, we'll cover how to manage sequences, and third, indexes. But you see that managing these objects is much more digestible than managing tables. We'll then discuss important practical guidelines and handy command variations. So let's get right into it. We covered column-level constraints in the last lesson. So picking up from where we left off, let's visit constraint outer table actions. You start by the action that adds table-level constraints. PostgreSQL allows you to add constraints to existing tables, which is particularly useful when your data model evolves or when you need to enforce new business rules. You can add various types of constraints to an existing table using outer table command. The syntax is always outer table, table name, add constraint, constraint name, and the constraint action that can be any one of these examples. Outer table customers, add constraint, PK customers, primary key, customer ID. Outer table products, add constraint, UQ products, SKU, unique SKU. Outer table orders, add constraints, check orders total, check, and then your formula total must be greater than 0. Outer table order items, add constraint, foreign key, order ID, references, orders, order ID. Each one of the constraints in previous examples were covered in table creation lesson, so we are not going to spend too much time repeating their particular syntax here. When adding constraints to tables with existing data, PostgreSQL verifies that all rows satisfy the new constraint. If any row violates the constraint, the operation will fail. When adding constraints to tables with large amount of existing data, validation can be time-consuming and potentially disruptive. PostgreSQL provides the not valid option for any constraint to be added. In this example, a foreign key constraint is being added to the order items table, but we are explicitly asking PostgreSQL to do not run validation checks when we append not valid to the end of the outer command. This command adds the constraint to the table's metadata and enforces it for new or modified rows, but doesn't validate existing data. This is particularly useful when, first, you are confident the existing data already satisfies the constraint, or you want to minimize downtime during constraint additions, or you plan to fix any violations after applying the new constraint, or unfortunately, you need to keep bad data in your database. That happens. Before adding unique, primary key, or foreign key constraints, consider creating an index first. This example creates an index on order items column order ID. Then we follow the create index command with an outer table that simply adds a foreign key to the same column order ID on order items. With this approach, the constraint creation becomes faster since it can use the existing index. Once constraints are created, you may need to modify them to accommodate changing requirements. You can rename constraints using outer table rename constraint action, from old constraint name to new constraint name. This operation is metadata only and doesn't require table scans or logs, making it safe to perform on even busier production systems. You'd be right if you say that for altering constraints, the right command is alter table, table name, alter constraint. However, Currently, only foreign keys can be altered this way, and even them are very limited, so we are not going to cover this now. While PostgreSQL doesn't provide a direct way to modify most constraint properties, you can always drop and recreate them with new properties. In this example, the foreign key constraint was dropped and re-added to where it was before, but we might be adding it with slight different parameters, for example on delete cascade. This example also covers the drop constraint command, so one more box tick. As we talked about cascade, the drop constraint command can also be followed by cascade. This time we are altering the table products drop constraint pk products, which as its name suggests should be a primary key, with cascade option. As you might expect, since it's not the first cascade we've seen in this course, this option is powerful but potentially dangerous. It will automatically drop any object that depends on the constraint being removed, such as foreign keys that reference this primary key. PostgreSQL allows you to temporarily disable or re-enable constraints, which is useful for bulk data operations. So after adding a constraint with not valid, you can validate it later when it's convenient. First, let's run a command that adds a foreign key with a not valid option. Then you run the following command: alter table, order items, validate constraint, and the name of our constraint. The validate action scans the table to ensure all existing rows satisfy the constraint. This two-phase approach minimizes table locks. The validate operation only blocks conflicting writes, not the entire table. We've used keys as our constraint examples, but let's cover them a bit more. Changing a table's primary key is a significant operation that requires careful planning. This deceptively simple command that drops and recreates a primary key on our products table can be disruptive because they require a full table scan to verify uniqueness. They rebuild indexes, of course. And finally, they may impact foreign keys that reference the primary key. As we've done before, foreign keys can be added or removed as our data relationships evolve. This is another example. To add a new foreign key, alter a table, order items, add constraint, fk order items products, foreign key product ID references products product ID. And to remove it, alter table, order items, drop constraint, fk order items products. When adding foreign keys to large tables with existing data, consider using not valid option followed by validate constraint to minimize disruption as we've just covered. Key constraints have significant performance implications. Primary and unique keys create indexes that speed up lookups or reads, but slow down writes. Foreign keys add overhead to insert, update, and delete operations as PostgreSQL must verify referential integrity. Frequent constraint validation can impact overall system performance. For high-throughput systems, consider these strategies. Create indexes before adding constraints. Schedule constraint additions during low traffic periods. Use not valid initially for large tables, then validate during maintenance windows. Now that we've covered constraint management, wrapping up the basic alter table commands, finally, let's turn our attention to sequences. As you recall from previous lessons, sequences are special database objects that generate unique numeric values, commonly used for primary keys and other incremental identifiers. PostgreSQL provides several ways to modify existing sequences to meet changing application requirements. Let's explore the most common operations. You can change how much a sequence increments with each call just by running alter sequence, sequence name, increment by, and the number you want to use. This is particularly useful when you need to adjust for increased data volumes, or create logical groupings with ID ranges, or even implement sharding strategies where different servers use different ID ranges. When you need to reset a sequence to a specific value, just run alter sequence, sequence name, restart with, and the value. This operation is commonly needed after data migrations, bulk imports, test data cleanups, or to prevent sequence exhaustion. Remember that resetting a sequence to a lower value than existing column data can cause unique constraint violations when new records are inserted. For consistency in naming conventions or security adjustments, you can also rename sequences. The command is just more of the same: alter sequence, old sequence name, rename to new sequence name. To change sequence ownership, easy. Alter sequence, sequence name like customer's ID sec, owner to application user, which is a new role. Sequence ownership determines who can modify the sequence definition. Typically, you want sequences owned by the same role that owns the table using them. Now, to control the range of values a sequence can generate, you can run alter sequence, sequence name, followed by the option you want to change. In this case, mean value, max value, and cycle. This is especially important for applications with specific ID formatting requirements, while when working with legacy systems that expect IDs with certain ranges. When it comes to removing sequences, the same concern applies as it requires careful considerations of dependencies and potential impacts. But if you need to forcibly remove a sequence and its dependencies, run drop sequence, sequence name, and cascade. This will remove the sequence and update or remove any object that depend on it. Of course, you should be careful because it can break default value expressions, it can disable identity columns, or remove dependent views or functions. This is why it's generally safer to let PostgreSQL manage the sequence lifecycle through a table's column definitions rather than manually. Dropping a sequence used by an identity column is different from serial columns. Identity columns have a stronger dependency relationship with their sequences. When a column is defined as generated as identity, PostgreSQL creates an implicit sequence that is owned by the table and cannot be easily separated from it. If you try to change ownership of a sequence that's used by an identity column, you get an error like, hey, I cannot change ownership of identity sequence. This is because identity columns maintain a special relationship with their sequences that prevents the sequence from being dropped or altered independently. This is actually one of the advantages of identity columns over serial columns. They provide better dependency management. With identity columns, you don't need to worry about sequence being accidentally dropped or altered as the sequence lifecycle is tied directly to the column. And you know what? When I attempted to drop a sequence associated with an identity column using cascade option, PostgreSQL will not allow the operation. Unlike the serial columns, sequences used by identity columns have a stronger dependency relationship that prevents them from being dropped directly, even if cascade. If you need to modify the sequence behavior for an identity column, you should use alter table commands to modify the identity properties rather than try to alter the sequence directly. To completely remove the identity property, you can use alter table, table name, alter column, column name, drop identity. Now that we've covered sequence management, let's turn our attention to index management. While indexes are crucial for query performance, they also require proper maintenance to ensure optimal database operation. PostgreSQL allows you to rename indexes using the alter index command. Just type alter index, index name, rename to new index name. This is a metadata-only operation that doesn't rebuild the index or scan the table, making it safe to perform even on busy production systems. It's particularly useful when implementing consistent naming conventions across your database objects. When an index is no longer needed or is being replaced, you can remove it using the drop index, index name command. This immediately removes the index and frees up the storage space it was using. However, it also requires an exclusive lock on the parent table, which blocks other operations until drop completes. For production environments where you can't afford table locks, PostgreSQL offers concurrently option. For that, add the keyword concurrently between drop index command and the index name. This approach allows all operations to continue while the index is being dropped. The trade-off is that it requires 2 scans of the index and takes significantly longer to complete. It's also important to note that concurrently indexed operations cannot be performed within a transaction block. When replacing an index, a common pattern is to create a new one concurrently before dropping the old one. Let's see how it works. First, we create new index without blocking operations with concurrently option. Then drop old index once the new one is ready. and rename new index to the standard name. This might sound useless, but that's because we are not discussing other types of indexes. And also because we haven't discussed that indexes can occasionally become corrupted due to hardware failures, software bugs, or unexpected data patterns. PostgreSQL provides the reindex command to rebuild a corrupted index. There are some convenient variations for reindex command. You can reindex an index, but you can also reindex all indexes on a particular table with reindex table, or if you are bold enough, reindex database to of course reindex all indexes in the database. Unlike drop and create index, the reindex command acquires an exclusive lock on the table, preventing other operations until it completes. For production environments, consider using create index concurrently approach that we saw before. When dealing with unique indexes that have become corrupted due to duplicate data, you need to resolve the data inconsistencies before rebuilding. Index management operations have significant performance implications. Creating or rebuilding indexes on large tables can be resource intensive. Each index adds overhead to insert, update, and delete operations, as we discussed before. Unused indexes waste storage space and slow down writes. Regular index maintenance is essential for optimal performance. Remember that while indexes speed up queries, they also slow down data modifications, so finding the right balance is key to overall system performance. Now that we've covered the core DDL commands for constraints, sequences, and indexes, let's discuss practical guidelines for applying these changes safely in production environments. These strategies will help you minimize risk and downtime when making structural changes to your database. One of the most important practices when managing database objects is making your DDL scripts idempotent, which means they can be run multiple times without causing errors or unintended side effects. For that, PostgreSQL provides conditional clauses, if exists and if not exists, that make many DDL operations idempotent. So pretty much all create commands and add operations to alter commands could be followed by if not exists, which means if exists, we don't want to run again. On the opposite side, pretty much all drop commands or drop actions of alter commands could benefit from if exists, as they don't break if the objects to be dropped don't exist. These clauses are particularly valuable in deployment scripts where you can't always be certain of the exact state of the database. They allow scripts to be rerun safely during development or when recovering from failed deployments. Before making schema changes, especially in production, it's crucial to understand their potential impact. So to analyze dependencies, you can run this daunting query. This is just an example of using system catalogs to identify objects that depend on what you are modifying. Let's revisit this query once you are more familiar with query operations. When it's time to apply changes to production, careful planning can minimize disruption. Use techniques that reduce or eliminate downtime. Add columns with default values instead of not null to avoid table rewrites. Create indexes concurrently to avoid blocking writes. Use alter table out constraint not valid followed by validate constraint. Schedule disruptive changes during maintenance windows. Monitor your database usage patterns to identify optimal times. Communicate planned maintenance to users in advance. Have a clear rollback plan in case of unexpected issues. Test the entire process, including rollback procedures, in staging environment first. Remember that even well-tested changes can have unexpected consequences in production. Always have monitoring in place to quickly detect and respond to issues after deployment. As we conclude our exploration of DDL commands, let's take a moment to reflect on what we've learned. Throughout these lessons, we've covered the complete lifecycle of database objects, from creation to management and modification. You now understand how to work with constraints, sequences, and indexes, giving you powerful tools to maintain the data integrity and optimize performance. We've seen how constraints enforce business rules and maintain data quality, from simple column-level constraints to complex table-level constraints and relationships. You've learned to add constraints safely to production tables using techniques like not valid and validate them after. We've explored sequence management for generated unique values, with operations to reset, modify, and maintain these critical objects. And we've examined index management strategies that balance query performance with maintenance overhead. You also learn how to use if exists and if not exists clause to make your operations idempotent. In our upcoming lectures, we will shift our focus from defining database structures to work with the data itself. We will explore data manipulation language or DML commands like insert, update, and delete, building on the solid foundation we've established with our DDL knowledge. Later, we'll dive into data query language or DQL to retrieve and analyze the information stored in our carefully designed structures. See you then.